So today we have the pleasure to have Raimon from the University of Valencia, and Raimon will also be joining us a few weeks from now in November. And today he will talk to us about quasi-normal modes in modified gravity using physics-informed neural networks. So please, Raimon, you have the floor. We have like around 1 hour, and feel free to ask questions during the seminar.
Okay. Okay, so thanks a lot for having me, especially in these difficult circumstances. It's a privilege to give the seminar here. Some of you will probably already know my one of these my lines of research, which relates these machine learning tools to try to use them in problems of strong gravity and general relativity. So since some of you might not know completely this topic about machine learning, or may have not seen my previous talks, I will start doing a small introduction to the kind of tools or the kind of machine learning techniques that we're going to be using. Of course, any suggestions for possible applications that you may come up to are very welcome, because this is what we're trying to do, trying to find new possible uses of these tools. So in this case, this is a pretty recent paper from April, where we actually extended previous tools that we had created to compute quasi-normal modes or perturbations of gravitational objects. But in the previous work, we were mostly concerned with general relativity, Kerr, and Schwarzschild black holes. In this case, we tried to extend it to this particular modified gravity theory, which is Einstein, Gilton, Gauss-Bonnet black hole solutions. And in this case, you have some added features or added difficulties. First of all, the equations are harder, but other than that, the background is already numerical, so you don't have an analytical solution for the background geometry. So this adds a little bit of complexity to the problem, making it a little bit more interesting for these neural networks. Right? Okay, so, it was done in this paper in collaboration with Daniel Duneva, Tony Font, and Stoicho, and the student of them, Jerwa Lia. Okay, so first of all, I want to start talking a little bit about what I mean by neural networks, for those of you who might still not be completely familiar with these kind of things. So this is like a first introduction, right? So I will start with this slide, where I kind of, like to be a little bit provocative in the sense. So typically in physics, we want models that have as few parameters as possible. And with these, we try to explain as much as possible, right? So there's this famous quote by John von Neumann that with 4 parameters, you can fit an elephant. With 5, you can make him wiggly strong. I mean, in the sense that 4 parameters are already a lot for physical theory. Instead, in machine learning, at least from the industrial perspective, it started as a way to fit things without the need of understanding them, right? So what you do is you fit whatever, you keep adding many parameters as long as they fit something, right? And as long as they fit it accurately. So for instance, GPT-3, the first ChatGPT that came to life, has this order of 10 to the 11 parameters, right? Now GPT-4 has like a few orders of magnitude more. Okay, so the idea here is I don't exactly care what these parameters mean as long as they fit whatever function, very complicated function I have. Okay.
But Raimon, the longer the larger the number of parameters, the better the fit, or in some cases?
Well, this is a tricky question. I mean, if you do it like in a crazy way, like without thinking too much, sometimes you can go into overfitting, right? So you will, in general, fit better whatever data you're training on, but it might not be a predictive model. You might use it on other cases that you didn't train on. Okay, so there's a whole field of things, a whole field of techniques to avoid that. Okay, so the idea is, well, at the end, we want to approximate multivariate function, typically a very complex multivariate function, like the whole of human knowledge in ChatGPT. So this is going to be a very complicated function, right? So these are typical tools that we use in mathematics, interpolating polynomials, splines, Taylor series, pares, orthogonal functions, and these are still very useful in many applications, even in machine learning, right? So you have something that's simple enough that you can be fitted with that, that's the way to go. Yeah. Okay, but the neural networks take a bit of a different approach, which is to start to, well, repeat many times something that proved to work, which is, well, first you take the most general linear transformation between two vector spaces. So you have this x0 with some input parameters, it's going to be very long, and then you want to get something out of that. So the most complicated linear thing that you can do is that just multiply the matrix, whatever it comes out, right? But then, of course, this can only store linear transformations, which are good, but not always everything you need, right? So people started adding these things that are a bit well, the magical part of this, which is called the activation function, which is a nonlinear function that you apply component-wise to your output vector, right? And this is called activation because they were, I guess, trying to mimic our actual natural neurons, right? That they spike at some potential threshold, and so they wanted to mimic that. If you call it each of these X components, you call it a neuron, then when you reach certain threshold, then the neuron activates, right? It becomes it takes a value of close to 1 instead of 0, right? Okay, so this is okay. I mean, this is actually called a perceptron. And for very simple problems, actually the ones that are where your classification task is divided by a hyperplane, then that is useful. But then people started, well, here first they started experimenting with many possible activation functions. The most famous and the first one was the sigmoid that goes from 0 to 1. This empirically we know the Dirac distribution. But then you can use hyperbolic tangents or things that are a bit more, not sure, kind of simpler, but they prove to work better. This is the rectified linear unit and leaky rectified linear unit. So you have all this kind of zoo of possible activation functions that have their advantages and drawbacks. Okay, so then people, since this was kind of a simple model, and it's already nonlinear, then it makes sense to start stacking them, right? So, I mean, you cannot stack linear transformations because you keep having a linear transformation. Once you have added some nonlinearity, it makes sense to stack many of them and repeat this operation, right? So this is what is sometimes called a multi-layer perceptron. Okay? And the thing is that even if this doesn't capture a lot of complexity in the data, then when you start adding these things, you can really fit very complex nonlinear behavior in a multi-dimensional function, right? Okay, so this structure of layers is usually represented here, like some sort of a conveyor belt. So you start with this. This is a kind of a vector, the input vector. And then you represent this linear transformation as these synapses that connect one layer of neurons to the next one. So each element in this W matrix kind of models the influence of one neuron to the neurons in the next layer. And then at each layer, you apply the activation, right? So you do this kind of things where you input here some very long vector and you get another long vector for at the other side. That does whatever transformation the neural network is put to do. Okay, so now here, this is an important question because with other interpolations, you always have an analytic or pretty much analytic way of determining the parameters of your model. So once you have the data that you want to fit, there's usually some kind of a linear system or whatever that you have to solve to determine which are the correct ways to fit whatever you want to fit. Okay. So instead here, we do a more, heuristic or straightforward approach, which is we define something that we call the loss function, which is a scalar, it's just typically a real positive number. That's some metric, some distance between what we are getting from the network compared to what we want to get. Okay, and the goal of the process is to make this as small as possible. That's it. So we summarize the performance or how happy we are with the behavior of the neural network in just one band. If it's small, we're doing well. If it's big, we're not doing well. Yes.
So when you go back to that, so when you said that you are measured the distance between what you get and what you want.
Yeah.
Something like that. So this is when you have something and you know the solution of something. But what happens when you don't know the solution of something?
Then, yeah, that's kind of our case. What the case I'm going to describe today. If you don't know, if you don't have something, the typical case is when you have some instances of data and how late, so you have what the solution should be. In other cases, you have to define that in some way that measures the performance. So how well you're doing. In this case, we are going to be solving differential equations. So in this case, this loss is like the right-hand side, it should be zero, right? So so you have a differential equation with some transformation over functions equal to zero. Well, that could be very close to zero. Okay, we want this to be small, but how do we do that? Especially because we have thousands, millions of parameters, so it's not something that you can do. You cannot even invert a matrix or something in a system this size usually. Okay, so what we do is this really simple trick, but it's actually very useful. Just compute the gradient of every component of every matrix or any parameter that you have in the model. You can compute this gradient, so the partial derivative of this loss with respect to that component. And this you can do because usually this loss has an analytical relationship to whatever you're fitting. So this you can compute analytically. And then you do like iterations by taking small steps in the direction, well, in downhill. So in the inverse direction of the gradient, right? You take whatever you had and you subtract this times on this epsilon, which is called the learning rate, which is, essentially models how fast you're descending, right? If this learning rate is very, very small, you're going to be very slow, but if it's very large, you can overshoot and go fast, right? As you will see, all of these names are really, really fancy, but they need, mathematical quantity. And then people started improving these things. You can add some inertia, like some momentum to the system, so it doesn't change direction too fast, blah, blah, blah. And these things are shown to help convert to minimum, like a local minimum. So a very famous one is this ADAM, which is adaptive momentum something. And as I say, it is not, I don't think it's even published, it's just notes in archive, but it's the most cited one. So it's something that really people use a lot. Okay. Okay, so now we need to compute this gradient, right? So as I told you, this can be computed analytically, but it can be computed in an efficient way, so that you don't lose. So you keep, storing all the information without losing anything. This is a bit of a dynamic programming kind of algorithm. So what you do is you start with the last step, so you compute how the loss varies with the last, like the output layer of neurons. Then by the chain rule, you can compute how it depends on this on these W's here by, just multiplying that with the chain rule, right? But now if you keep computing more and more gradients of previous parameters, previous waves, essentially you're repeating whatever you already had. So this piece is this piece, and you just add the extra term in the chain rule. If you keep storing all of this is an extremely efficient way of computing the gradient without losing the information that you already had from previous layers. And if you look at it, you are what this sorry, this is like the whole bunch of terms. So if you look at it, when you were evaluating, like generating some result with the network, you start here and you keep going, calculating in this direction. So you go forward. This is called a forward pass. But when computing the gradient, you're actually going backwards. So you start at the end and keep computing gradients towards the input nodes. And that's why this is called back propagation. Okay, it's just a chain rule, but in a smart way. Okay, so at the end, I like to show the dictionary where I connect this machine learning terms to mathematical terms, right? So at the end, when you talk about these fully connected networks, these are just a bunch of these perceptrons, like this operation. When we say deep learning, we mean that we have many layers, like say typically more than 2, okay? Training or learning means finding a minimum in this loss function. Okay? Some people complain to me that, hey, you're not learning anything really, especially in this mathematical cases, right? Well, that's the way that's how we call it. And then backpropagation is just applying the rule with dynamic programming concepts, right? Okay, and of course I have to mention that these are not all the networks that we have, because these are sometimes you have so many input values that it's more useful to kind of restrict the kind of relationship that you can have with the neural network. So for instance, when we have something that's kind of shift invariant, like images, like a car here is the same as a car there. I mean, I don't really distinguish between different types of cars depending on their position. So we use these convolutional neural networks that replace like a general linear transformation by a convolution transformation with some filters or whatever. And these are, well, these are some of the first networks that were used in this sense. And then for sequential, like natural language, time series, or gravitational waves, if you're interested, you can use these kind of things that have memory, right? Recurrent neural networks where you get the output and you fit it back to the same network at each time step. So these networks have some sense of memory. They are kind of aware that the relationship is sequential. So you have this recurrence, you have attention mechanisms, and these attention mechanisms gave all of these transformer models that are now ruling the world, like this GPTs or whatever. Okay, so now that I've done the first introduction, let me move to the actual physics. Okay, so here, this is the new part, say, with respect to previous talks that I had done. Here we have this extension, this extension of general relativity where we add this scalar field and we couple this Gauss-Bonnet scalar with the scalar field with this some non-trivial function f of phi, right? So there's the action, simple, and we actually consider two possible couplings. This kind of Gaussian, and these are the one we call quartic coupling, whatever. And as you will see, these have like pretty different behaviors, or the solutions of these. If you want to see the actual solutions, these appeared first in this paper by Daniel and Luis Vasquez and collaborators. Okay, so we have they have a code that actually produces black hole solutions for these kind of theories. It's not a unique solution, so you have a whole family of solutions for each coupling. And now we want to perturb that and get the quasi-normal modes. Okay? And we will do that with this machine learning magic. Okay. You have this perturbation equation that looks pretty horrible, but at the end is pretty much the Wheeler equation. These are strictly symmetric, by the way. Wheeler just with some extra functions that you would set to 1 otherwise. Okay. So what do we do? Okay, so we take this equation and we do some modifications to it. So first of all, we do this we find these parameters that are kind of dimensionless rescalings of things. And we take this phi, which is the perturbation master variable, and we factor out say the singular part, right? So the parts that summarize the behavior close to the horizon or close to infinity. So there are these two constants, gamma and delta, that depend on the surface gravity and on the mass of the black hole. So they depend pretty much on the follow-up rate of fields, right? And we reshape everything into this form, which is, linear combination of derivatives of this new completely regular variable, this g. So we have derivatives of this, powers of omega, the frequency. And we have these things, these are coefficients that depend only on the background quantity. So each of these a's is actually a radially dependent function, but we compute it once with whatever background solution we have, and that's it during the whole training of the solution, right? So we're gonna look for some g that satisfies this equation, but along the whole training, these a's are fixed. They just depend on the background. This is important because this can be pretty complicated, and the computation of these might be a bit costly. Okay. And of course, this becomes a regular equation if you set these a's to whatever it has to be. Okay, I review some possible methods that I've seen I'm pretty sure I'm missing many of them, but some of the typical methods that people use on the equations. This is kind of the simplest one, but it's not very efficient to say. So you can evolve the equations and see the follow-up of the fields, right? And then you get, at least the first mode you can get that way. Some people use shooting. Some people try to do these semi-analytical forms where you express the equation in this tortoise coordinate, and you get some potential barriers, so you can do kind of a scattering problem. There's this WKB, aesthetic interaction methods, spectral methods. These are very powerful. I'm a huge fan of these methods, as you probably know. Where you can get many modes with a lot of precision. And then I've done like very strange things like expanding in a number of dimensions like my PhD. And these things can also be used to obtain a mode with some precision, right? Even in 4D. Okay. So here what we are going to do is we have that equation. By the way, this factor is important because, essentially it helps the convergence. You can check which factor it is, because when you set this to the Schwarzschild case, you see that you have this factor. This is a common factor, and this actually helps with the convergence even in Schwarzschild, right? So and then we have this, and then what we do is we set some normalization condition. Of course, this is a linear equation, so we need to normalize it somehow to fix the solution, otherwise we'll get any multiple of the same thing. So the way we do it is this very strange thing. That's called the hard enforcement of boundary conditions, which means that we take whatever comes out of the network, we multiply by something that becomes 0 at 1, and then we add 1. So this is just a trick so that anything that comes out of the model of the neural network already satisfies this boundary condition or this normalization condition, no matter how crazy we go with the solution, right? So we don't have to worry about that anymore. Okay. So and this actually is, so all the extra terms in the chain rule that appear because of that are managed by the machine learning environment by PyTorch. So we really don't have to work anymore to do that. We just add it there, and the software handles everything. Okay, so this is pretty much kind of a flow chart of how this thing goes. We have the background solution that comes from other codes that have, in principle, I don't have to know anything about this code. From here, I compute these coefficients. These coefficients are already fixed for that solution. And then I started iterating. So with this, I compute with this equation, the equation loss, which is pretty much the right-hand side of this equation. In this case, we are evaluating in many points. So I take the mean square of this, so the mean of the squares at each of the evaluation points. Okay, so I compute the loss, and then I do as before. So I use the atom optimizer to modify the weights and the biases, so all the coefficients in the network in the physics informed neural network. And here I get an updated version of G. So this is the solution and the omega and the frequency. So I keep doing that many times. Each time I get a smaller loss, and when this converges, hopefully I should have the solution, right? Or well, one solution, not all of them. Okay, so here this is an example. Actually, this is for care, so it's general relativity, but in this case, not spherically symmetric anymore. This is not real time, but almost. Say there's about a factor of 2 of the time that it takes to train that model, and this we actually showed in this previous paper of ours. So here you can see the target value. So this is the accepted value for this spin in care, and you can see the evolution of this is the radial profile and the angular profile of the solution. We separate the variables, and this is actually how the loss keeps decreasing with these epochs. Again, epoch is a very fancy name for the iteration. Okay, and you can see that how this omega, the frequency and the separation constants, actually converge, and they converge very close to the right? As I said, this is a little bit faster than the actual computation, but it's not something dramatic. Questions so far?
So you have a couple from the previous
Yeah, then go back. Yeah, you want?
yeah, so the
Oh.
background solution
Yes. The double sum is just a way of saying so n is for the derivative, they go up to order 2. And m is the power of omega. It's just a way of writing it in a complex way.
the background solution is well.
Yes, it's correct. So I haven't agreed. I can interpolate, but yeah, just yeah, that's a difference with respect to the relativity, for instance. Okay, this thing loads. Okay, so well, that's the data. Okay, so I present some results for this. Actually, for the first model, that the quadratic coupling function. And so here I have several things. So the blue so these blue lines are the GR solution. These the green dots are the reference modes. So the modes that were published in a previous paper. In this case, for this particular coupling, we already had the solution sometimes, and so we could use this fact to actually check that our network was doing well, and actually to kind of gauge when we can trust the network and when not, which is a tricky question. So as you can see, so these orange solutions of ours really match the previous ones. In this case, we have to be careful because there's at some point where this solutions lose hyperbolicity because we're out on a theories. So at some point you can get solutions that are not no longer hyperbolic. So the equations of motion are no longer hyperbolic, and then everything should break down, right? So in the previous paper, they managed to get the modes pretty much up to that point, to this vertical orange line. In our case, as I will discuss now, we see that they start to fail a bit before. Okay, and this was very useful because we could see all the symptoms that we were getting when the solutions were failing. Okay, so let me see. Okay.
So sorry, Raymond, can I ask a question on the previous slide? Can you clarify again what the difference between the orange and the green points? Not sure if I fully understood.
Oh, yeah. No, the green points are done with, are in a previous paper, say without me, done by, I think they used some version of WKB method. So it's not machine learning at all.
And the orange is using machine learning then.
Exactly. And my machine learning computation is the orange ones that are, say, denser, but they don't reach as far.
Okay, thank you, Raymond.
Okay, so this is ideal. Yeah, here I put that list. You can see that the errors are really tiny, up to, so this for the quadratic moment. So the errors are usually below 0.1%, something like that. So we can trust 3, 4 significant figures.
When you say errors, you're comparing with the solution.
In this case, yeah, I can only compare these particular values because I had the previous solution. Later on, I will not have that. Okay, but here I can see that, well, the errors are pretty small until I get close to the hyperbolicity loss.
And the solution is failing because the solution is increasing or something else is happening? Because you have large numbers or because something else is happening?
I mean, I don't completely know the ultimate causes of this, but at the end, when you don't have hyperbolic equations anymore, it doesn't even make a lot of sense to compute modes, right? So yeah, the gradients become large, but if you compute the potential, like the economic potential that corresponds to that scaling problem, it becomes like it has like a very large negative spike. It has pathological things. I don't know exactly. Pretty sure the mathematicians will know.
Yes, can you go back to the previous slide, please? Yeah, so that vertical, that line, marks the breakdown of hyperbolic.
Yes. So that's the actual. I mean, I didn't compute. I mean, I didn't compute myself, but it's comes from background solution. It has nothing to do with the model. Okay, so whenever the background
So
solution.
they did manage to get some solutions close to that line.
Yeah,
But you didn't.
I didn't. Right.
Why?
So this I'm not sure. It might be because of my implicit limitation of this method, or just a lot of translation. I mean, because of course I have to adapt their data from their code to mine. Maybe some interpolation in between methods of.
Can you say you don't get a solution? Is it just because of pressures or is it?
No, usually I will discuss that. Here I'm not plotting the wrong solutions, but usually what happens is that it diverges. You start getting omega. So wait. Okay, so something I wanted to discuss here is that here when you see that the error, in this case we can use the fact that we know the right solution. You check that, okay, when the error becomes very large, then the actual loss that you have at the end of the training is large as well. Okay, so for small errors, you have very small losses, which means that the differential equation is very well satisfied. But if the solution, even if it sort of converges here to a wrong solution, it converges to something that doesn't satisfy the differential equation. And this is a hint, right? Because this we can know, or we can always know. We have this loss that's just the right hand side, and if the right hand side is too large, then we know we can say, okay, the solution is not okay. So we try to quantify that, and for instance, here we decided that the loss has to be say around lower than 0.1. Okay, so if you fix that threshold, you can say, okay, whenever the loss goes beyond that, I cannot draw solutions anymore. And so we did this kind of plots. Okay, so this is a plot of loss versus error. You can see that the relationship is kind of power law. Not perfectly, but so lower loss means lower error, larger loss, larger error. And so if you plot the loss along this family of solutions, this one line is again loss of hyperbolicity, and you see that GR goes through perfectly well, but the other one fights really kind of almost diverges to this point. So if you set some threshold, this is kind of arbitrary, but we chose 0.1. You set that and you say, okay, if it crosses here, then we can trust all of these solutions, but not each one. Okay, and this is actually a very powerful tool because with this machine learning techniques, you don't usually don't have a completely obvious way of gauging how much you can trust the solution. You don't have what very well defined conversion. Yeah.
So how do you initialize the
Yeah, so the first, there are several ways to do that, but usually what we do is we start randomly, like the weight conversions randomly, but then we give like the previous values when we move along the curve, like on the family solution.
But what happens if you do the initial solution as being the two one calculated with another method? For instance, you have the previous solution. What happens, for instance, with the loss solution?
Oh, you give the
right solution.
the right solution. Well, then I guess the one is gonna be super small, and probably even gonna get worse, because I mean, this optimization is gonna drive it probably to whatever we end up having. So with, yeah, I guess you will start with a tiny loss and then might even increase. Okay, so yeah, since we don't have any proper convergence testing or anything like that, these kind of symptoms are really useful. Okay, and here we move to uncharted territory. So the theory is that nobody has calculated, so we don't know, we cannot tell if we are doing right or not, right? But as you will see, we can estimate that as well. So this is the quartic model, so it's the same, but it has this four here. So here we have several families of solutions. This has some nice things. First of all, is that well, it doesn't connect to GR. So the solutions, the branching solution that we get here doesn't asymptote to GR in any of the limits. And then we can vary this parameter and get these different solutions with different positions of hyperbolicity laws. And well, we tried that. I mean, we kind of did some checks just for safety that other methods like I run a spectral code and it agrees. But in this sense, we are kind of risking it here, right? So we did that the same again. We plotted the loss versus the parameters, in this case the mass, the parameter along the branch solutions. And again, we get that GR always stays below the threshold, and the others they spike whenever they get too close to their fate, right? And this actually makes a lot of sense, because if you actually plotted these solutions, they really deviate from the trend. So in the sense, we can pretty much say that we are, well, that we can trust the method. Now, some advantages of this with respect to other methods are, well, first of all, that they seem to adapt very well to the medical background. It's really nice, because sometimes it can be challenging for other methods if you don't have a very good prediction with the background. And then something else, actually, what I was telling you, that we can use the previous solution to train the next one. And this gives some stability to the method to convert to something that makes sense, right? Other methods, sometimes like spectral methods, get some of them right, but some the ones that for some reason have somewhere to error or something just go crazy, right? But in this sense, we are restricting, we are already telling the model, okay, looks great, but it has to be somewhere near. Okay. So let me, I think, yeah, I have like 1, 3, 4 questions. Let me give some conclusions or some ideas that I got here. As I said, any other ideas are welcome, because this is a very experimental field. Well, the first idea is that it is actually possible to use these techniques. It's a bit, I mean, the precision is not amazing, but it's pretty good. The time is a bit larger than with other methods, but it's still manageable. And we can use this networks like a bit of a black box, a universal solver for ODs, PDs, and these PDs can contain parameters, eigenvalues, as many as you want. And at the end, we are dealing with fitting parameters, so you can add as many pre-parameters as you want, and as long as the system is constrained and all the time, you should converge to this. The implementation is really, I mean, it's quite easy compared to other methods because you have all these machine learning environments that already compute all the gradients for you. So you pretty much just define whatever function you want to fit. And you have all the work already done by you. So you can use this PyTorch or TensorFlow or whatever. And these environments even contain parallelization or acceleration routines that you can use well straight out of the box. So you just say, okay, I want you to run this on a GPU, and it runs immediately. You don't have to change pretty much anything, right? Or even more than one GPU. And this is really cool because I mean, as you probably know, much of the computation funds are going towards GPU clusters and these things. So running these things on these machines is something that we have to consider, especially if it doesn't require any extra development, right? Here, as I said, I mean, the performance is pretty good. I mean, the solution is, at least for numerical backgrounds, is pretty much comparable or the same as other methods, as usually the precision is limited by other factors like the background solution. So yeah, the performance is pretty good. It's just that it takes a little bit longer, not much, but a bit longer. And of course, I mean, if you had a super good precision for the background, then that might be a limitation. Okay, so yeah, so the conclusion is that okay, we have this new tool. So of course, if anybody comes up with any idea of how to adapt this to other systems, that's a pretty straightforward and available way of that. Okay, thanks for your attention.
Thanks a lot, and also for keeping the time. So now we have plenty of time for questions.
Just a quick question. When you mentioned that it takes just a little bit longer, so what are the typical times and what is the mean time that it takes?
Yeah, well, I mean, this depends a lot on how you implement it and which problem you have. In this case, as I said, it's kind of that order. Say each mode might take 10-20 seconds, maybe like that. I mean, of course, if you do it with a spectral method, it will take milliseconds. But it's not something that you have to wait for years, you know.
And in terms of computational cost, so it takes that time on a GPU.
Yeah, that takes. I mean, that you can run. It would take that time even on a CPU. With a GPU, the funny thing is that you can run. So I was actually using a single GPU, but I was using I was running all the families at once. So GPU has more than enough memory and thread to do many of these computations together simultaneously. Yeah.
I have a question actually regarding one of your projects back in Valencia, because I know that when you were using for copper labs, you have this method pins, and you compare the speed using the speed of the performance of pin versus spectral method. Sometimes spectral method is way too much faster than.
Yeah.
How do you know that?
I mean that I wasn't really. So in that particular project, I was focusing on the spectral method, not on the pins. So I don't know exactly what technique they are.
So you think that you can improve the speed for pin?
For the pins, I mean, you have to be careful not to. I mean, if you need like many overtones, many modes for many cases, maybe it's not sometimes the best case. And well, you have to be careful. Short answer is that you never know. I mean. If the problem is so simple that you know how to solve with another method very fast, I would say no with that. Don't start doing these things. This I would recommend for kind of particularly difficult equations or things that you don't have anything implemented or you don't know how to do it. Like a first attack. Yeah.
So for this last model, we do not have an error estimation from the direct comparison of
No.
different networks.
No, in that case, no.
But you're still using the threshold on the loss function from the previous model. model. How do you know that this threshold is going to be valid?
Yeah, that's a bit of an extrapolation. Yeah, this you have to trust. I mean, when you look at the solutions, I'm pretty sure that it's okay because they start behaving. I mean, the change is pretty abrupt at this threshold. But yeah, this is something you have to. Yeah.
We have also questions on length, so maybe Carlos.
Okay, let me. So they have to read
Hello?
it.
Can you hear me?
Yes, I can hear you.
Okay, thank you. Thank you very much, Ramon, for the nice talk. The sound on my side was not perfect, but I think I could hear most of it. My question is the following. So, what's the prospect of computing in, say, in the Kerr case, the quasi-normal modes, but without the separation of variables using this method, so solving the PDEs?
Oh, solving the Kerr case?
Yeah, just because it's the case where you know the result and you can actually separate, so, but without actually separate.
Yeah, this is something I have on my mind. I've had it for quite some time. My guess is that it should be doable as long as you know exactly what boundary conditions to impose. So in the Kerr case, it's obvious because it's just a product of whatever we had in the separated variables. In other cases, well, yeah, it's what I say. It's I guess the main difficulty is to define exactly what boundary conditions you want to impose. But apart from that, I've done some experiments like in 2D, like in PD, eigenvalue problems, and kind of works usually.
But for the particular quasi-normal mode case, since you know the result, it would be a very nice benchmark, right, to do it in the Kerr case. So do you have any preliminary results about that?
Not quite. I mean, I have some eigenvalues, but not for Kerr. This is some project that I was actually thinking of doing sometime soon. Yes.
Okay.
Well,
Okay. Thank you. Thank you, Raimon.
Pedro also had a question on that.
Yeah, yes, I have. Thank you, Raymond, for the very interesting talk. So my question, I apologize if my question was already answered during the talk, but because of the sound quality, sometimes it's hard to fully understand what's being said. So I apologize in advance if this question was already addressed. So Raymond, in a kind of provocative fashion, although this method is certainly very interesting, what is the main advantage? So playing kind of the devil's advocate here. So what's the main advantage of using these kind of machine learning methods to compute quasi-normal modes compared with more traditional methods? So can you elaborate a little bit on this?
I mean, it's always a question that's always hard to answer, but there can be different reasons why you decide to do that. So the first one is that conventional methods are, particularly in this kind of problems, they are not always fail-proof. So if you have a very noisy background or something that's very strange, some of the methods may not work perfectly. So these networks sometimes seem to be particularly robust, like, so they kind of always work. I mean, they can lose precision, but they tend to converge to something, okay? And the other possibility is that at the particle level, that implementing one of these things is like really fast. I mean, once you know how to do it, is a matter of a couple hours, while doing other things might involve more development work, especially if you want to say parallelize or run it on GPUs or whatever. Okay.
So I understand. So I think my take from your reply is that it's very flexible and robust. So especially if you want something quick, I guess it's the method to apply them.
Yeah, exactly. I think it's just like a first approach. Then if you decide to, devote a whole year of your career to computing these, maybe you should start considering using other methods, right? But as a first approach, or if your differential equation say that, I don't know, say that you have an equation that has more than one parameter that you have to fit or something like that. then
Well,
that is
I guess-
even.
I guess some of those more traditional methods, some of them they might need an initial guess. So in that regard, using these machine learning methods, I guess, would be a fast way to also obtain a very good initial guess as well. That you can later use to obtain better precision if needed. Okay. Thanks, Raimon.
You're using Python, right?
Yes.
And have you tried to use other language? Because I think Python is native in Flow, right? And for some other methods are using other languages, are using double flow. And you're summing errors because you don't have double precision.
Yeah, this is I think you can do higher precision even in Python.
Yeah, but you have to specify in every interaction, no I got 128, when you have to specify in every interaction.
Well, yeah, maybe. I'm not completely sure about that. The limiting factor actually might be the machine. So you have to be careful that some GPUs, well, actually most of them, you have precision. So you might have to use one of these Tesla or whatever that have larger precisions, yes. But language, I think it's low.
More questions? I also have, so, how many layers do you have in the network and how much does it depend on this number?
Yeah, exactly. So we did a study on that. Usually it does, for this is actually a pretty simple problem, so it doesn't depend much. I mean, as long as you have reasonable amount of neurons. But we are using, I think, 2 hidden layers right now. So it's like 2 hidden layers, so it's 4 like inputs, 2 hidden and then output. And then I think the hidden layers have like 256 neurons, like 156. But I mean, as I said, you can use a smaller one and probably gonna work to be pretty good.
And my other question, which also will be related afterwards, but to compute this right-hand side, that is basically your loss function, how many, I mean, what is the method to compute this right-hand side? How many points do you have?
Yeah, exactly. You evaluate on a grid of points. In our case, we have, I think it's about.
Well, I mean, I don't know the exact number, you know.
No, I think it was about, we used about 1,000 points, but in this case, it was a lot because, well, the solution was a bit tricky, but for care, I think we used 100.
Okay.
And they don't even have to follow a grid, you can just throw points here and there.
Okay.
And you evaluate over that and take the main square error.
And does it change if you change like the kind of a convergence, usual convergence to the number of points, but I guess.
Yeah, that's a tricky part. It doesn't have a mathematical, it doesn't have a convergence in the mathematical sense. Because the interpolating function is not something that has a well-defined degree or anything. So it converges, but it's not something that we can say to the fourth order or whatever.
But if you increase the number of points of your grid, do you need to increase the number of neurons or?
I haven't played a lot with that, but there's a kind of a rating. I think usually you have to, yeah, you double one, you double the other. Several theories. The thing with that is the mathematical theory is really almost non-existent. So I mean, people have done things, but very complex.
Yeah, and I guess I mean the right equation could be also the like the norm that you're using. To take so the mean square, but
yeah, even if that was wrong. Actually, for some applications for classification techniques or things like that, they usually take things that come from information theory, like cross entropies or something like that. Not always that help you know.
More questions? Any more questions on Zoom? Okay, so I think we can thank Raimon again. And we'll meet tomorrow for the next seminar.
Okay, thank you very much.